In this section, we're going to discuss complex data and structures. We're going to learn about data type precedence, discover how to deal with multinational data, and understand how to query hierarchical data using the hierarchy ID data type. SQL Server attempts to convert operands to the same data type. And data type conversion can be either implicit or explicit. Rules of precedence determine the outcome of conversions. And these rules dictate that when evaluating operands of different data types, the data type with a lower precedence converts to that of the higher one. If that's not supported, however, the attempted conversion will actually throw an error. In this chart, you can see the data type precedence order, and you'll notice that the user-defined data type has the highest order of precedence, while the binary data type has the lowest. T-SQL gives us a cast function that'll help us convert data types. The syntax is cast, and then you, in parentheses, give the expression as the data type that you want to cast it to. That expression must be any valid T-SQL expression, and the data type has to be a valid T-SQL data type. The length value is given for character-based data types. There's another function in T-SQL called try-cast. That's really kind of a wrapper to the cast function. It's a little safer. However, it's not a reserved keyword, so if you have IntelliSense on, it'll think it's an error. The syntax is as follows. Try-cast, where the expression is any valid T-SQL expression, and again, the data type is any valid T-SQL data type with the optional length for character-based data types. If the try-cast fails, meaning that the conversion from one data type to another is invalid, it will return a null value. So let's take a look at a couple of examples here. Here we've declared a variable amount as a real, and we're going to assign that variable amount to the expression you see there. When it's time to print out our result, we need to cast that amount variable, which is a real, into a varchar, a character, so that we can concatenate it to our print statement. Here you can see an example of using the try-cast. It's essentially the same as the one above, except as I said earlier, it's a wrapper. If it doesn't like the conversion of our variable amount into a varchar, it'll actually return a null. So let's go to SQL Server Management Studio and take a look at an example. So here we are in SSMS, and we're going to take a look at using the cast and try-cast functions, as we need to sometimes convert one data type to another. And the first example we're going to look at here is the select statement. Let me highlight that for you. What we're going to do is we're going to do an explicit conversion using the cast function. We're selecting the last name and first name of an individual, and then we are going to put in parentheses here the business entity ID, their employee ID, so to speak. And because that's cast as an integer, we're going to need to explicitly change that data type, and we will use the cast function to do that. So we are going to cast that integer as a variable length character, and because the end result of this is all character based, this will work just fine because we've taken the time to explicitly cast that integer, making sure that SQL can deal with it. So let's go ahead and execute that, and we can see here that we are getting back in the parentheses the employee ID as expected. Now, you may be tempted at some point not to do that, thinking that SQL might work like some of the CLR languages, and you'd be wrong. SQL needs things pretty much explained to it, and if we're not very careful, what will happen is we'll produce some errors. And you'll see here that it's the same select statement, except we've taken out the cast. So SQL's going to go along here and try to work with this, and all of a sudden it's going to be working with character-based data, and then it's going to run into this integer, and it's not going to like it. So let's go ahead and fire that up. And of course here it sees when we're trying to cast the character data back to an integer. And you might say, well, wait a minute, that didn't make any sense. We were working with character data, ran into an integer, and it's balking about trying to convert a character to an integer. And that's because, remember, the rules of precedence that the data types have, and when SQL tries to convert those data types for you, it's going to go from lowest to highest. So what happens here is that the character-based data has a lower precedence than the integer. So it was trying to convert that. So let's finish this example up by talking about the try cast. Now, try cast is not a reserved word, and you can see here that while it's not underlined, I have the IntelliSense turned off for that just because I find it a little annoying that it doesn't recognize that. But if your settings aren't identical to that, you'll see that that is underlined and it doesn't know what it is. And that's because it's not a reserved word. But what that function does is it's going to attempt to cast this as a varchar, and if it fails, it'll return null. So it's a little bit safer than the straight cast. It's kind of a wrapper to that function. And what I've done here is I've just wrapped that into a coalesce. And what the coalesce does is say, hey, if by chance this try cast fails and returns me a null, then I'll put not available or not applicable in those parentheses. This will actually cast just fine because we know we can explicitly cast an integer to a variable length character, so that'll be just fine. But again, try cast, a nice little wrapper. And now let's go ahead and execute this select statement. I'm just going to go up here and highlight this and execute, and we get back the results that we expect. Again, we knew that casting the integer to a variable length character was going to be just fine, but you might want to check out try cast. As I said, it's a nice wrapper to the cast function and makes your data conversions a little bit safer. So now we're going to discuss working with multinational data. Character-based data can be tricky to work with because at times we may end up working with different languages. And when SQL needs to sort and compare strings, it has to look at the specific rules for the languages and regions where people speak those languages in order to know how to handle it. The encoding, sorting rules, and other region-specific settings is called collation, and they're essential to the organization and operation of SQL Server databases. So the key term here is collation, specifications detailing how to sort and compare character data based on the rules of a particular language and region. SQL Server supports collation settings at different levels. The first is at the server level. All databases, unless you specify otherwise, use the same collation as the server. Individual databases, though, can have different collation settings. And finally, columns within a table can use specific collations. So what do you do when sets of data are stored in different collations? T-SQL gives us a collate clause to deal with that situation. We use collate where the collation name must be a literal, indicating either a specific Windows or SQL Server collation. And database default forces the collate clause to use the collation setting of the current database. Here's a warning though. SQL creates tempdb each time the service starts and uses the same collation setting as the model database. Working with data that has a different collation than tempdb could cause problems. When we have expressions that reference data of different collations, SQL has to figure out how to evaluate a result. SQL Server classifies the objects involved and determines their collation category. This is also known as their collation label. This chart details how SQL Server assigns those collation labels. The first type, called coercible default, is a T-SQL string variable, parameter, literal, or function that does not take character input but returns character output. If it's declared in a user-defined function, stored procedure, or trigger, that object receives the default collation of the database where its parent object resides. We then have something called implicit. The resulting collation of the expression passed is the collation defined for the column within its table or view. Explicit This is the case when we actually use a collate clause to specify the exact collation we want to use. And finally, no collation. When the operations between the data have conflicting collations, the result is no collation. So how does SQL actually evaluate expressions that have different collation labels? We then have to talk about something known as collation precedence. If the collation label is explicit, that will take precedence over implicit, and implicit will take precedence over coercible default. An error will occur when you attempt to combine two explicit expressions with different collations. Combining two implicit expressions of different collations causes a no collation result. And when evaluating an explicit expression and a no collation expression generates an explicit result. Why? Because you're using the specific collate statement. Combining a no collation expression with anything other than an explicit expression results in a no collation label. So here's a chart that details how each of the combinations work and what their results are. Let's go to SQL Server Management Studio to take a closer look at collation. So in this example, we're going to take a look at how SQL Server deals with collation. And what we're going to do is we're just going to create a table that has two columns. Each of those columns are going to have assigned to them different collations. This way we can insert some data into those columns knowing that the collations are different and see how SQL Server reacts. So let's go ahead and create the table. And so now we have a table with two columns, two different collations. Now we're going to insert some data into that table, just a single row. One row was inserted, and what we've done is we've chosen to insert words that have the same spelling except for an accent. Right there, we can see the difference. And so, how does SQL actually deal with the fact that if we go and ask for retrieving data where the Latin column is equivalent to the Colombian column, what are we going to get? And what we're going to find out is that SQL throws this error. It can't resolve this because we defined the table using two different collations, as we can see up here. And so it's trying to compare two things that are using two very explicit different collations. So what we can do is rewrite that statement. We'll use an explicit collation statement here indicating that we should collate this column using the Latin general case insensitive accent insensitive collation, which essentially means that it's going to ignore that accent up there. And if we do that, sure enough, we get back a row of data. So just a very quick example to show you how you can use the collate statement to work with multinational data. Now we'll discuss working with hierarchical data. Hierarchical data is something developers work with all the time. Consider an organization chart, bill of materials, or a sales order with all its line items. They're all examples of hierarchical data. Expressed in database terminology, it's kind of like the parent-child, header detail, one-to-many, self-joins, etc. Conceptually, hierarchical data is a tree structure, and any given node can have 0 or more child nodes. The challenge that we face is how do we implement this structure within a database? There are basically two methods for storing these relationships. One is called multi-referential. This uses multiple columns within a single table to represent relationships between parent and child nodes. There's also the adjacency list. This uses a single column within a table and only stores the link to the row's parent record. The multi-referential approach uses a single table with a column for each level within the structure. For example, if we have an organizational chart that's 5 levels deep, then that table needs to have 5 columns to represent relationships. And while this structure is easier to query, it's somewhat limited and inflexible. If we change parent-child relationships, then we might have to update many rows. And if we ever need to add levels to the structure, we actually have to redesign the schema of the table. To help reduce complexities of working with hierarchical data, SQL Server has a hierarchy ID data type. And that data type is a .NET CLR user-defined data type that has these characteristics. It actually stores a node's position, and it's optimized to represent a tree structure. It's very compact. 100,000 nodes, each with an average of 6 children, only requires 40 bits to store the node's position. It uses depth first order indexing, which means children are stored next to their parent. And it exposes methods supporting arbitrary insertion and deletion of the nodes. The hierarchy ID data type does, however, have limitations, and some of those include that the data type only represents the node's position and not the structure. Doesn't guarantee any uniqueness of the values. And SQL won't enforce relationships like it does for primary foreign key entries. That's your responsibility as a developer. When you want to work with the hierarchy ID data type, you have to get familiar with its methods. getAncestor returns the hierarchy ID of the nth ancestor of the node. getDescendant. That'll return a child node of the parent. The arguments can be either null or the hierarchy ID of the parent. getLevel returns an integer representing the node's depth within the structure. getReparented value. That allows you to move a node from its old root to a new root. getRoot returns the root of a structure. There's also an isDescendantOf method, and that returns true if the selected node is a descendant of the parent. Parse, that converts the string representation of the node's position to a hierarchy ID. Read is an internal method, and that reads the binary representation from the binary reader. ToString returns a string representation of the node's hierarchy ID. And write, another internal method, writes out the binary representation. So how does one implement a basic hierarchical structure, such as an organizational chart? Well, let's go to SQL Server Management Studio and discover how. In this example, we'll take a look at how to use the hierarchy ID data type. What we're going to do is we're going to create a table to store employee information and basically store the org chart. And what we're going to do is create a procedure that's going to allow us to insert the employees into that structure as nodes the way that they're organized within the company. And I show you this example because organizing the nodes in that hierarchical structure is really your responsibility. So this will show you how you can determine the root of the structure, find the appropriate place based on the parent-child relationship, where to put a node and how to get it inserted. And once we have this procedure defined, then we can use it to insert the nodes representing the employees, and then we can select that data back out. So let's start by first defining the table. here we have our create table statement. Pretty straightforward. The only thing here is you can see that we're storing the employee ID, that's our hierarchy ID data type. We're also storing the level. Remember that the hierarchy ID has a method called getLevel, and we'll store that because it'll make it easier for us to query that table later. If we want to get everybody at the same level, we'll be able to do that very simply. So let's go ahead and create that table first. And that was successful, and now we're going to do most of the work here in creating this procedure. And what we're going to do is we're going to create a procedure that allows us to add an employee to that structure. We're going to take in the parent code, what the employee code is, first, last name, and title, so that'll match up with our table structure. And what we're going to need to do is check the parent code. We have to make sure that the parent code is either sent to us and is legitimate, or if it's null, how we're going to handle it. So the first thing we're going to do is say, hey, if it's not null, if someone actually passed us in the parent code, then we need to go get that record. So we're going to get the employee ID from the table where those two match up. The employee code matches the parent code sent in. And that's how we're going to get children. We're going to insert the children that way. If we don't get a parent, that really means that we've sent in the first node or the root of the structure. So we're going to assign the parent ID the result of the get root. So we will get the first node in the structure, and that's what this little branch is going to do. Now, once we've completed that section, we need to figure out what the position is of the node. And what we need to do is figure out what is the left and right child to the node that we're trying to insert. And so what we'll do is we'll figure out what the minimum employee and maximum employee ID to the left and to the right, where they both share the same parent. That's the get ancestor. So do we have anything that we can find where this particular node that we're trying to insert has siblings? And if we can find that, then we'll find the left and the right child, and what happens is we can then go ahead and insert this into the table. And we're going to place into that table the employee. The get descendant method is going to be used. Again, following the convention, we'll have the left and right child passed in. That's how we discovered the position using that up here. And with the values in the table now, we can then return, and we have a generic procedure for putting in our employees into some structure. Again, the key is we find out whether we're dealing with the root or a parent node. Once we have the parent node, we figure out, let's see if they have any siblings, and now we know where to insert that row. So down here, we're going to start executing this stored procedure, and we're going to start adding in our individual employees into the structure. And you'll see here, here's the first one where we are not passing in a parent ID, so that will become the CEO record, and then the other records will follow. So what I'm going to do is, let's go ahead and create that stored procedure. Okay, we'll go ahead and execute that so this procedure gets created. Then we'll come down here and actually call that stored procedure n times here to load our data. And you can see here from the output that that was successful. And now what we're going to do is retrieve the rows from that table, and we should see that it's organized appropriately because that stored procedure put them in the order that we wanted by calculating the children and its descendant or parent. And here you can see we have level 1 followed by the level 2s, 3s, and 4. So the hierarchy ID is useful for storing hierarchical data. The issue that you're going to run into, though, is it's still not all that straightforward in managing it. The responsibilities for inserting and balancing that tree are yours, but this gives you an example of how you could construct a generic stored procedure to handle that detail for you.